Okay, well, um, good morning, everybody. I think, is it morning still all across the country? I hope so. It's definitely morning here in Victoria. My name is David Thistle. I'm along with Helen Joseph. We're have been the past chairs of the Arctic Special Interest Group of CMOS. And so we've operated this session at CMOS Congresses and at ArcticNet meetings for a number of years now. And so the session is titled The Changing Arctic, Science and Policy Studies. And you can see on your screen the agenda for today's session. And we will, so we'll have a number of talks. I think we've got 5 oral papers, and then we've got 2 short preview presentations. These would be 5 minutes of the related posters that are going to be presented tomorrow in the poster session of the Congress this year. So I think I'd like to introduce my co-convener, Helen Joseph, and Helen, over to you.
Thanks very much. I don't know that I necessarily have much to add to David's introductions other than welcome everyone. Thank you for joining us on this first session. I know it's still morning here in Eastern Ontario, and it's definitely very early morning, I know, in the BC coast. So welcome everyone. David and I will be playing a little bit of alternating co-chairing here during the session, and hope that presentations can be kept, as we said, to about 11-12 minutes. We'll give you a 1-minute warning, and then we'll have time for some questions afterwards with a short break occurring during the session, and look forward to hearing the presentations. Now, David, if you introduce the first presenter, then I can introduce you as the second one here. Thank you.
Okay, I'd be happy to do that. So our first presenter is Knut von Salsen, and Knut's with Environment and Climate Change Canada, right here in Victoria as well. So another person up early this morning. And Knut's going to present a paper on policies to limit air pollution are key for successfully mitigating Arctic warming. Knut, over to you.
Thank you, David, and good morning, everyone. I have a quick question in the beginning. I just noticed that the program showed half an hour for my presentation. I'm not sure how much time I actually have.
Yeah, the program got scrambled up, unfortunately. So yeah, we'd like, in order to fit all the papers in, if you could try to get through your talk is in I was going to say 12 minutes, but maybe that's not realistic if you planned for a half-hour talk. But
no,
yeah.
I planned for 15 minutes. So
oh, good. Okay,
that's good. Good. I'm
okay.
glad. It's always easier to talk longer.
Yes.
Okay, so I would like to present results from a recent report for the Arctic Monitoring and Assessment Program, AMAP, which was requested by the Arctic Council. So this is really focusing on policy here, and I hope it will be clear how the science can contribute to policy in this area. And so the focus of this report is on policies for air pollutants and how they affect Arctic climate. And so I'm going to present some key results and an update on that report. And the report is currently in press, but the summary or a summary for policymakers is available on the web if you're interested. And the report should come out in a few weeks, I'm assuming. Okay, so I'm primarily going to talk about particulate matter in this presentation, but I'm going to mention methane as well and other short-lived climate forces. And excuse me, particulate matter consists of matter that warms and cools the climate. So there's black carbon and sulfate in particular. And the reason we're interested in particulate matter is also that it affects human health, and this is well documented. So there are different aspects that we wanted to cover in this report. And particulate matter is particularly interesting for policymakers that are interested in Arctic climate, because the lifetime of particulate matter is only a few days. But that means that control measures have pretty rapid impacts on the concentrations and therefore on climate impacts. And so I mentioned that there's cooling and warming components, and the warming component, black carbon, is of interest in this report. But we've also looked at organic carbon and sulfate to some extent. And so black carbon gets transported to the Arctic, where it can deposit on snow, and then it warms the snow through absorption of solar radiation, and that also leads to either snowmelt or heating of the lower atmosphere. And one example is the dark snow over Greenland, and there's a photo here from Jason Box on the right. And I should mention, this is not just black carbon that contributes to the dark snow. There's also algae in the snow and other things that are going on. But the deposition of black carbon on snow is certainly a concern in this report. So in order to address policy questions, we are using 4 new emission scenarios that were developed for this report. The first one is the current legislation scenario. And so this scenario assumes full implementation of current national and regional air pollution legislation. And so that's our baseline scenario. And it's similar to SSP 245, which is used by IPCC. And then we have 3 mitigation scenarios. And these scenarios are a little different from the SSP scenarios. They look at really very strong reductions in air pollutant emissions. So this is the driving mechanisms here are really air pollution. So the question is, how can we reduce air pollutants by introducing technologies that are actually feasible? So these are technologies that already exist. And the MFR scenario captures those changes. And then we have a few variations on that scenario. We have MFR STS scenario and also the CFM scenario. And I'll talk about those scenarios in more detail. So for this report, we mainly looked at those 4 scenarios, but we've also considered the SSP scenarios in work that we did after the report. And this slide summarizes the SSP scenarios as well as the AMAP scenarios. And so the SSP scenarios are shown as with full lines, and you can see that the SSP scenarios cover a wide range of CO2 emissions and methane emissions. And you can also see that the AMAP scenarios, which are the dashed lines, produce really very strong reductions in sulfur, black carbon, and organic carbon emissions. And so the message here is that these aerosol or particulate matter components are projected to decline very rapidly in these sustainability scenarios. And declines are also obvious in the SSP scenarios. It's not just the AMAP scenarios. You can see improvements in all of the scenarios for these components. So in order to simulate changes in climate and air pollutants, we're using a so-called AMAP emulator, and I'll talk about that emulator on the next slide. And the basic idea is really to use regional emissions. So we have these emission inventories, and we can analyze the emissions that are coming from certain regions. For example, we're looking at the Arctic Council, and we're also looking at Arctic Council observer states here, which you can see on the map. And then we're using those emissions and converting them to temperature changes and also changes in air pollutant concentrations. And the tool that we're using is this AMAP emulator. So this is essentially a box model of heat, air pollutant, and carbon cycle processes in the atmosphere. It's very similar to what IPCC is using. So the key objective is really to compare the impacts of regional anthropogenic emissions of CO2, methane, and air pollutants on climate and air quality. And it's actually quite difficult to obtain those from full Earth system model simulations, because we're talking about relatively small emission perturbations, about relatively small changes in radiative forcing and climate. And so we need some extra tools to address those. And the tools that we're using are based on absolute global and regional temperature change potentials, HGTP or ARTP. Again, this is similar to what IPCC is doing, but we're putting more emphasis on regional temperature changes. So we're breaking down the temperature response into different latitude bands, and the Arctic is one of those latitude bands. And so this builds partly on what IPCC is doing, but it's also building on earlier reports for AMAP. And we're using results from Earth system models to constrain the emulator simulation. So we're using radiative forcing perturbations that we recorded from Earth system model simulations. And so this is a relatively simple approach. It doesn't account for natural climate variability. It doesn't account for changes in naturally emitted air pollutants or land use or CFCs. And we can really just focus on those air pollutants that we're interested in isolation. And so here you can see some results. The plot on the right shows temperature changes that we simulate with the emulator. These are the color bars for the Arctic on the left and global temperature changes on the right. And so this is the temperature difference between 1995 to 2014 and 2050. So we're just looking at changes over the next few decades here. And then again, we have those 4 scenarios. And for the current legislation scenario, or CLE, let's focus on that. We can see that the emulator is projecting a temperature increase of about 2 degrees over this time period to 2050. And most of that warming comes from increases in CO2 or CO2-related changes in climate. But there's also a contribution from sulfate, which is the orange bar. So sulfate cools the climate through scattering of radiation in the atmosphere. And that means that as emissions are declining, that means radiative forcing is also declining, and that actually leads to a warming impact over this time period. And so we're talking about the unmasking of earlier warming through emission reductions of sulfur here. And that's actually a pretty substantial contribution to Arctic warming, as you can see from our emulator simulations. And then if you look at the mitigation scenarios, at the MFR scenario in particular, you can see that there's actually a large contribution from black carbon emission reductions. In particular, since black carbon is warming the climate through absorption of solar radiation and through deposition on snow and ice, that means that reducing those emissions leads to a cooling impact on the simulated temperatures. And so that partly counteracts the warming impact from reduced sulfur emissions. So that's essentially the story here. We're seeing substantial benefits from emission reductions for black carbon and to some extent methane as well, although that doesn't really show up too well in this plot. And I have a summary here that hopefully is a little clearer. So just looking at all of the scenarios that are available to us, including the SSP scenarios, we find that Arctic warming improvements by 2050 from deep emission reductions for black carbon and methane are actually similar to the warming improvements that one would get from CO2 emission reductions. And so if you look at the range, at the ranges between the simulations, so between the MFR and the CLE scenario, there's a warming reduction of 0.3 degrees that's associated with black carbon. And so we're just talking about the Arctic here, and about 0.2 degrees from methane. So the total climate benefit for the Arctic is about 0.5 degrees if those emissions are reduced aggressively compared to current legislation. And that compares to about the same number, about 0.5 degrees from CO2 emission reductions. And we're getting that by comparing the SSP 126 scenario with the SSP 585 scenario. So those are the scenarios that are available to us and that have been simulated by a lot of Earth system models. And again, the numbers are comparable, but keeping in mind that we're looking at a relatively short time period here up to 2050, and we are looking at the Arctic. So these numbers are very specific to those conditions that we're looking at. And we further find that regional Arctic warming is particularly affected by regional emissions from Arctic Council countries. Because those emissions are close to the Arctic, that means transport processes are efficient and deposition on snow is efficient. So overall, Arctic warming is about 6 times more sensitive to black carbon emissions from Arctic Council countries than from global sources. And we also looked at the global impacts, and of course they're smaller, but they're still noticeable. And another portion
sorry to interrupt, Newt, but
yeah.
you've got about 1 minute remaining.
Perfect, yeah. This is essentially my last slide before the summary. So we also looked at mortality simulations. So Susan Annenberg from George Washington University and other people used tools to simulate mortalities. And it's clear that mortality is going up over time, and this is due to the aging of the population. That's the case for the current legislation scenario. With maximum feasible emission reductions, there are actually huge benefits. So hundreds of thousands of deaths could be prevented by introducing those technologies. And so my summary, so again, particulate matter pollution is declining globally. We see that in all of the scenarios. And that leads to a warming impact from declining sulfur emissions due to the unmasking of earlier warming. We find, though, that cutting black carbon globally is among the most powerful actions that are available to slow the pace of Arctic warming over the next 20 to 30 years. And so if you put that together with methane, it's about the same benefit as aggressive CO2 emission reductions over that time period. And it would be particularly efficient to target black carbon rich sources in Arctic Council countries. But of course, if you look at the longer term, if you look at the time period to the end of the century or even longer, then it's of course necessary to have additional emission reductions. So then CO2 becomes much more important. Thank you very much.
Great. Well, thank you very much, Knut. And maybe we have time for one question and then hopefully some more time at the end of this session. So does anybody have a question?
Perhaps while someone is thinking of a question, I just wanted to acknowledge and thank you actually. Canada, and particularly Canadian scientists, have often played very high profiles in the Arctic Council working group work, and particularly AMAP work. I know that Robbie McDonald, who passed away over the wintertime, was instrumental in a lot of the oceanographic work done by AMAP. And I'm just pleased to see that you're involved with the AMAP work and that this, I know this great high standard of research is still recognized inside of Canada. So well done.
I have one quick question. I found it interesting that your work looked in specifically at the contributions of emissions, especially in regard to black carbon from the Arctic Council countries, and the much bigger effect that those countries immediately adjacent to the Arctic have on these effects. So is there more detail on that in terms of, and looking forward, is there more information about the particular countries and their contribution to the problem and how their mitigation strategies and projections might play into this outcome?
Yeah, we cannot resolve individual countries at this point in time. We can only resolve the impacts of emissions from large regions on the Arctic, such as the Arctic Council, and that has to do with the simplicity of the emulators. We only account for radiative forcings over broad latitude bands. So I don't think those tools exist yet.
Oh, okay. Thank you.
So David, do you want me to go ahead and introduce you and we'll carry on through the session?
Yes, please.
I don't see any questions there. So again, thank you very much for, did Paul Kushner have a question?
I'll ask it in the chat, and because I recognize the time's passing. Thanks.
Okay, thanks. And maybe we'll have a moment, as David suggested, at the end of the session. So without further ado, thank you to our first speaker, and we'll move on to David Fissel with our second speaker. Many of you, I think, know David from his long involvement with CMOS, but David works with ASL Environmental Sciences out of Victoria, BC, so he's another early riser. Over to you, David, and again, I'll give you the 11-minute, 1-minute warning. And anybody in our participants, please go ahead and type your questions into the chat for us. Thanks.
Okay, thanks, Helen. And can you see my screen?
Yes, we can.
Oh, good. Okay. Well, I'd like to start by acknowledging my co-authors for this talk. And let's get started by looking at the objectives of this work. And this is this talk today is building on a longer term project in which we've been analyzing year-round continuous measurements of sea ice velocities over a 20-year period going back to the late 1990s. And the measurements have been obtained in the southeastern Beaufort Sea, the Canadian Beaufort Sea, at the sites shown in the map on the upper right, in particular at the mid-shelf site, Site 1, and at Site 2. And the analysis today that I'm going to present is a detailed analysis of the wind force ice dynamics during the reduced ice motion period of winter and early spring over two particular ice seasons out of the 20-year record. And the data are collected, as you can see in the schematic diagram, using subsurface moorings that are operated for year-long periods, mounted on the seabed, and the ice velocities are measured with an upward-looking sonar, the acoustic Doppler current profiler. So the sea ice velocities have been well studied and are characterized as shown in the map on the left. This is from a paper that Kent prepared a few years ago, and it shows the annual mean sea ice velocity field over the Arctic Ocean, especially the Western Arctic Ocean, and its anticyclonic or clockwise large-scale circulation pattern, which is known to be the dominant forcing for this ice velocity field are the winds, including that large high-pressure system, the Beaufort High, in this region. But the actual working of WIDS occurs over much shorter time periods at synoptic timescales with durations of about 2 to 8 days. And you can see on the right a histogram showing the duration of individual wind episodes or events for easterly winds and westerly winds, which are the dominant wind directions in our study area. So here in this next slide, we're looking at winds and ice speeds over the 20-year record, and these are plotted by month. The wind speeds are shown on the left, and we see for wind speeds, there is very little in the way of seasonal variability, and there are also the trends in the wind speeds over this 20-year period are very small or negligible. The story is very different for ice speeds. There are two measurement sites shown on the right, and we see a marked reduction in ice speeds during the winter and early spring months compared to the fall and then later spring period. And these reduced ice speeds in the ice season, winter, early spring, are associated with the occurrence not only of generally reduced speeds, but the occurrence of no motion over time frames of hours or a few hours up to a few days. So the ice actually stops moving for significant short-term periods. The 2 years that we've done our detailed wind event analysis on, I just wanted to show in this slide some context for those and compared to the 20-year record. And so these 2 years have lower ice speeds, and which are shown on the upper panels, and they have typical to higher numbers of no motion days. So the analysis that we've done is based around these individual wind event periods, which is shown in the upper left here. Here you can see the wind velocity, the hourly east-west wind velocity, and the individual wind events that are derived from that as the blocky looking line in the figure. And the key parameter that we're using to characterize ice to wind response is the response factor, which is the average ice speed divided by the average wind speed over each individual wind event. And we're going to focus our look at the results on what we call major wind events. These are wind events that are very much from the east or the west. They're within, the wind direction is within plus or minus 45 degrees of the easterly or westerly directions. And here you can see on the right all the individual wind events over each of the 2 years. And there's a lot of them, and you can see how they vary in direction. So when we look at the this ice to wind speed response factor, as you can see in the graph in the bottom here, it's pretty clear that there's 3 regimes in the ice to wind response. The first one is in the fall and early winter when the response factors are high, and we define that as being greater than 1.8%, but they go up to 3, 4, even a 5% in that period. And they are, and then they resume again in later in the spring, that free drift regime, and they are highly variable. And there is no apparent bias in this time period between easterly and westerly winds in terms of the response factor. The other very notable regime is from early January to early May, and that's what we call the reduced response regime. And this is where the response factor is less than 1.8%, but still above 0%. And we see many events which much reduced response factors, and again, a high amount of variability. And then within that reduced response regime, we have some what we call zero response events. And this is wind events in which the ice velocities are 0. There's no motion over the duration of the wind event. So we're going to look at some kind of statistical tabulated results from these wind events here. And as I mentioned, nearly all the events include at least some no motion ice speeds. And here you can see a segment of the data with these wind events and the ice velocities shown. And when we look at these major events separately for each of the 2 years, you can see in the table we've tabulated the number of easterly wind events and westerly wind events. And in these 2 years, there's more westerly wind events than easterly. But we see also a difference in the response factor between the east and wind events. And the east, the wind events from the east have a larger response factor than those from the west by 1.13% on average to 0.88%, indicating larger internal forces for winds from the west in each of these events on average. And here we're looking at another segment of the data, and now we're looking at patterns within the wind events. And we see 2 patterns that are noteworthy. One of them is a pattern of no motion developing later in the event. And if you can see my cursor, you can see this westerly wind event here. About halfway through the event, the ice motion stops completely, and another westerly wind event with the same pattern. So this pattern of no motion developing later in the event is dominated by westerly wind events, 37 versus only 5 for easterly wind events. And another pattern that's noteworthy is a delay in the resumption of ice motion at the start of the event. And you can see an example of that for this easterly wind event in the middle here, where the ice motion doesn't start up. It had been 0, and it stays at 0 until about a day into the event itself. And this occurs more often for easterly wind events than for westerly wind events. And when we look at no motion events, there's not as many of those, but some examples of those are shown in this figure. And in the red, where the red blocks are those no motion events. And when we look at the 2 years, we see that there's more no motion events under westerly winds than for easterly wind events, 5 versus 2. And the no motion events were most often preceded by westerly winds in 6 of the 7 cases. So this is my summary and slide. So we've described from this detailed analysis of over the 2 years of the ice response to winds, that there's the 3 different regimes: the large free drift response in the fall, early winter, and then resuming again in later in spring, and then that reduced response regime from January to April, early May, where the response factor of ice to winds is much smaller, and that includes these no motion wind events. And so to close, the implications for sea ice dynamics are westerly wind events are subject to larger internal ice forces than easterly winds, which would explain why there's the lower response factor for westerly wind events. And the reason for this is, I think, pretty straightforward. It just reflects the larger internal ice force that's developed when ice velocities have a shoreward component, which is the case, as you can see in the little figure here on the left. For westerly wind events, there's the effect of the rotating Earth. The Coriolis effects are such that the resulting ice velocities have a shoreward component, and the opposite is the case for easterly wind events, which the ice velocities would have an offshore component and therefore develop less internal ice stress. So there's a large variability, though, that we see in the ice to wind speed ratio among the events. And so it's not just that effect I've talked about above. There's something more complicated going on here. And we think that reflects the variability in internal ice stress, and that's associated with the nature of sea ice being highly deformed due to fracturing and leads, and the very highly variable morphology of the sea ice. And so the next step is in these events to look at trying to quantify the sea ice morphology for the events, and using satellite and also some data from those upward-looking sonars which measure ice drafts. And so that's where we plan to go next. And thanks for your attention.
Thank you, David. I didn't even have to give you the 1-minute warning because you were moving on to your summary
that's
slide.
good.
So I'd encourage, if anyone has questions, please go ahead and drop them into the chat. I see a little bit of discussion going on. Okay, but we have a question from Ada, I think. Sorry if I missed this, David. How do you determine east-west wind events? For example, do you choose a certain range of wind directions to be an east or west wind?
Yeah, I probably went over that too quickly, Ada, but what we do is we take the wind record, which we're using a high resolution wind data set from Environment Canada that's was developed for the Beaufort Sea. And then we just the dominant winds are easterly and westerly. So we just plot the east-west wind component, and then we we look at, based on that, we identify the individual wind events. So when the wind changes from west to east, that's the start of an easterly wind event. And then when those wind components go back to a westerly component, that's the end of that event.
Okay, thanks, David. Given the time, I'm not sure maybe if we should carry on.
No, we probably should move on, Helen, I think.
Thanks, and we've got another quick question here, maybe,
Oh,
David.
okay.
Yonique has asked, how did you separate the current effects?
That's a good question. We do have information on ocean currents, but in this study, we did not deal with the ocean current effects. And we have done some previous work where we've looked at that. But in these particular moorings, from our earlier work, wind is definitely dominant in moving the ice. There aren't any large ocean currents under the sea ice that have a major effect on the ice motion, especially during the late winter to early spring period. So.
Thanks again, David, for your presentation, and thank you also to our participants for putting some questions in there for us all. And just to comment on the work of ASL, you've got such an impressive depth of observations going back so many years. I think many would be envious of the work that you've been doing in the Beaufort and the data that you've got at your disposal. But so thanks again. Now I guess we're moving on to our two posters that we have. What's the order again, David? We have Madeline.
Well, it actually got changed, I think. So in the program that was presented the beginning of this, I think we're going to start with Madeline and then go to Caitlin. Yes.
So Madeline, can you do you screen share and if you've got a presentation on your poster, you've got 5 minutes. I see you're there. That's promising.
There we go. Yeah, my name is Maddie Myers. I'm a PhD candidate at Queen's University with Dr. Laura Thompson. And the goal of this project is to understand watershed sensitivity to glacier hypsometry and rising equilibrium line altitudes in the Canadian Arctic. So the NCAA hosts 14% of the global glacier ice volume, and studies that focus on this area typically focus on melt volume and less so on the spatial distribution of melt. And so what we're trying to understand is how is the accumulation area ratio changing and how is the ablation area changing under rising ELAs to better understand how the spatial distribution of glacier melt flux from this region will change as the ELA rises. So in order to do this, first we derived watersheds and we ended up with about 10,000 watersheds across the region. So we then grouped them by basin or channel. And then for each of those basins, we classified or we calculated the glacier area, the hypsometry, and the current equilibrium line altitude. And then once we had these kind of baseline values, we were able to simulate how the accumulation area ratio changed and how the ablation area changed as the ELA rose. And so the regions that we ended up with, we had 12 different basins within the NCAA region. And we can start to understand sort of what we might expect to see as it relates to sensitivity. So there was a paper by Furbish and Andrews that sort of classified glacier sensitivity based on where the equilibrium line altitude was relative to the elevation of the glacier bulk area. And so in our top plot of figure 3 here, we can see that the ELA is below the glacier bulk area, and this tends to be our northernmost glaciers. And so these glaciers should be, in theory, the most sensitive to rises in the ELA. Then we have a few basins where the ELA is more or less equal to the glacier bulk area elevation. And these tend to be our westernmost glaciers. And then lastly, we have glaciers. So these are our least sensitive glaciers where the equilibrium line altitude is above the glacier bulk area. And this tends to be our southernmost glaciers. So we can already see that there's a spatial distribution to the sensitivity of these glaciated basins to rising equilibrium line altitudes. But we can quantify this sensitivity by then looking at the change in ablation area or the change in accumulation area ratio with the change in equilibrium line altitude. And so if we look at the change in accumulation area ratio per meter ELA rise with respect to the change in ELA, as it currently stands, we can see that, let's see, Norwegian Bay is the most sensitive to, or the accumulation area ratio is the most sensitive to a change in the ELA. And our northernmost glaciated basin is the least sensitive. So that's our northern Ellesmere region up here. But this changes over time, or as the ELA rises, I should say. And we can also look at the sensitivity of the ablation area with rising ELAs. So that's figure 4B down here. And as it currently stands, the most sensitive basins are Ellesmere Southeast and Jones Sound. And then we get to the Greeley Fjord glaciers and Ellesmere North glaciers. But as the ELA rises, we see that Greeley Fjord and northern Ellesmere glaciers start to increase in their sensitivity, while our more southerly glaciers start to decrease in their sensitivity. And so what this plot is showing here is that if, let's say, the equilibrium line altitude is 200 meters greater than it is today, and it rises by 1 meter, we would expect to see the ablation area increase by about 110 square kilometers. And so kind of the point of all of this is to show that under a small ELA change, we might start to see a shift in the bulk freshwater output from the NCAA from the southerly glaciers to coming more from the northerly glaciers. Thank you.
Great. Thank you, Maddie. It's, we're going to hold questions right now. But I think there are some in the chat, and and we'll move on to the second brief poster summary presentation, and this is by Caitlin McNeil, and the title is "The Impact of the Decoupling of Wind and Sea Level Pressure on Sea Ice Motion in the Nares Strait." Caitlin?
Hi, sorry. Can everybody hear me?
Yes.
So I focused on characterizing the winds through the Nares Strait during extreme ice area flux events. And I'm sorry, I'm a graduate student under Professor Kent Moore. I said that while I was muted. And I was looking at ice flow through the Nares Strait. So I was looked at ice area flux, which we found using Sentinel-1 data. And we can see that when we look at the ice area flux through the strait with this defined gate at the northern terminus, that there's extreme positive and negative events where we expect from the climatology of the area to see ice flow that's primarily positive down the strait. And so to look at these extreme events in more detail, what we did was we looked at the wind forcing on these events, and in particular the meridional winds. So to look at this, we looked at the correlation and the composites of the area, you can see here. So I looked at the 2 sigma above and 2 sigma below the mean of these events, and you can see that in the 2 sigma below, when we have the negative ice area flux, which means that the ice is traveling northward up the strait, which is against what we expect climatologically, there's a strong correlation between the meridional winds and the ice area flux. Whereas when we see the ice coming down the strait, we don't see this same correlation happening. And this was somewhat surprising. So we looked instead towards the climatology of the area. And this showed us that there's actually a pressure gradient going up the strait, which we expected to see coming down. This has previously been shown by Samuelson et al. To see this pressure gradient for the wind to come down the strait, but it hadn't been shown for these negative flux events. And so what we're looking at now is whether this is a true representation of what's happening, or maybe there's a multiplicity of synoptic scale events or environments that arise here that would cause there to be such a weak correlation in the area for these positive ice area flux events. And ultimately, what we hope to better understand from this is why the ice area, what is causing this forcing on the ice to come down, and whether it can be primarily blamed on the winds, or there's other things that need to be taken into consideration. And so the next steps with this will be looking at whether the ERA 5 data, which was used for the winds in this case, is fully capturing what is happening, or we need to look at a finer resolution of wind speeds to better evaluate the area. And if you want to find out more, the presentation or the poster session is tomorrow. Thanks.
Great. Thanks very much, Caitlin and Maddie. So at this point, we're supposed to have a short break. We're running about it. We had a break recommended of 10 minutes, but we're running 5 minutes behind schedule. So I think maybe we should carry on so that we don't cut any of our remaining 3 speakers short. I guess there are on the poster presentations, there will be a chance tomorrow, as I understand it, when you at the poster session for more questions on your posters. But is there any quick questions right now for Madeline or Caitlin before we move on to our next speaker? I think there was something in the chat. But...
Yeah, David, there was one in the chat, and I also put in the chat the reminder about the poster session tomorrow, 11:45, where Maddie and Caitlin will be available if there's more questions. But yeah, I can maybe read it out too. Manny had a question, kind of 3 parts. I guess they were asking why. This is the one for Maddie. Why ELA greater than glacier bulk case or the least sensitive, as you've mentioned? And they're wondering, is this maybe meaning percentage wise? If that question isn't clear to Maddie, then maybe we can just have the microphone turned on quickly to ask that question, maybe.
I think I understand what you're getting at, but if I do a bad job at answering, maybe we can chat in a bit too. But the reason that they're the least sensitive is because I don't know if the screen will be reversed or not, but when the equilibrium line altitude is above the bulk glacier area, a rise in it isn't going to be much of a change in the, or sorry, not the ablation area, but the bulk glacier area. There's not going to be as much of a change. Whereas if we're sort of in this range, we will see a bigger change because there's a greater area near the ELA, if that makes sense. But I'm also happy to chat with you in a bit during the poster session.
Thanks for responding to that question. But yeah, there is more time tomorrow. Because that answers her question. Good. Okay. Thanks again to our students for your posters. I appreciate that. David, do you want to introduce Kent? It looks like Kent is the supervisor for Caitlin, if I have that right. So we're kind of keeping it in the U of T family here.
Yeah, that's a good segue into the next talk. So this talk is by Kent Moore, who's a professor at the University of Toronto. And the talk is titled Thin and Thick Ice in the Beaufort Sea, a New Regime with Enhanced Mobility. Kent?
Great. Thank you. Can you all see my slides?
Yep.
I'd like to first of all start by acknowledging my collaborators on this work. So Mike Steele, Ashel Schweiger, Jin Zung, and Kristen Leiter from the University of Washington. So this work was really motivated essentially by this image right here. This shows summer, so July to September, sea ice age anomalies in sort of the Western Arctic in 2020 and 2021. And as you can see in both of these summers, there was, if you like, anomalous thick or old ice in the Beaufort Sea, and we're sort of interested in understanding why that was the case. Sorry. So if you kind of look over the past number of years, the Beaufort has undergone this transition. It used to be characterized by multi-year ice, and now it's one where in the summer, there's lots of open water. So this, again, is just the climatological sea ice age, again, back in the early part of the record, and then more recently. You can see this dramatic sort of, if you like, transition from an area which had quite a bit of multi-year ice to now one where there essentially is a lot of open water in the summer. The same thing is true if you look at ice concentration. Again, early part of the record, even in the summer, there was quite a bit of ice in the Beaufort, and now we're in this region where there's lots of open water in the Beaufort. If you look at sea ice thickness, this is from biomass, you essentially get the same sort of notion where now we've transitioned from a region which had quite a bit of thick ice in the summer to one where essentially the ice is much thinner and there's even open water present. I just want to draw your attention to this area up here, which is called the last ice area. And it is the area which has the oldest and the thickest ice in the Arctic. And it's presumably the region where ice will last the longest in the Arctic. And so one of the interests in this work is sort of understanding the connection between the last ice area and the Beaufort Sea. There's been quite a bit of work in this area. We wrote a paper back a number of years ago looking at the winter of 2017 when the Beaufort High collapsed. Bab et al. Sort of followed that up with looking at the impact that had on sort of ice cover in the Beaufort Sea. More recently, Ballinger et al. Documented another collapse of the Beaufort High in the winter of 2020. And then more recently, Mallet et al. Kind of looked at the winter of 2020, the winter of 2021, and they wrote this quite interesting paper. And I just want to kind of comment on this sort of last sentence from their abstract. This atmospheric circulation pattern drove older ice from the central Arctic into the lower latitude Beaufort Sea, where it was more vulnerable to melting in the coming warm season. And so they suggested this sort of setup may lead to unusually high summer ice loss of the Arctic's remaining store of old ice. So essentially, we want to sort of look and understand, in fact, whether this is the case and how it varies from year to year. So there's sort of one of the things I want to talk about are the processes that are responsible for this old and thick ice in the summers of 2020 and 2021. Then what is the relationship between the sea ice in the last ice area and the Beaufort Sea? And then finally, is there a relationship between the cool season ice volume transport into the Beaufort and summer melt? So these are time series, again, focusing on the Beaufort Sea. This is mean sea ice thickness going back to 1979. And this is essentially the ratio of the volume of sea ice in the Arctic to the Arctic in total. And both of them show a decrease over time. And so we did a variety of sorts of fits. We tried linear fits, we tried piecewise linear fits and step functions. And again, what we found was that if you essentially did a step function fit with a breakpoint in the year 2006, you essentially minimized, if you like, the RMS error between the fit and the observations. And so what this, if you like, argues then is that there's been this transition recently from a regime where one had thick ice, to one where the ice is much thinner. And similarly, essentially the Beaufort's contribution to the entire ice volume of the Arctic has decreased by about a factor of 2, again, with a transition sometime around 2006. And so in this case, there's a number of years that are outliers, 2013, 2020 and 2021 are outliers in the sense that they have thicknesses, or if you like, ratios that approach the values during the old ice area, the old ice regime. So again, there's evidence of this regime shift. And then, if you like, the last couple of years, in addition to 2013, have been years where the ice has been quite a bit thicker than will be normal in this new ice regime. So just focusing on these two winters, what I'm showing you here is the anomaly of the winter of the sea ice motion and sea ice thickness during the winter of 2020 and during the winter of 2021. And as you can see, there's quite a remarkable difference in these two winters. So in the winter of 2020, one had this cyclonic circulation, which essentially would advect sea ice from the Chukchi into the Beaufort and from the Beaufort into the last ice area. This is an anomalous situation, and this, in fact, was the result of the collapse of the Beaufort High during this winter of 2020. Winter 2021 had a very, very different kind of pattern. We had now this sort of typical anticyclonic ice motion, which would have advected essentially ice from the last ice area down into the Beaufort Sea and then out into the Chukchi. So essentially, one can see those dramatic differences. And this leads to quite large differences in the anomalies in the spatial distributions. So you can see that in 2020, we had essentially ice piling up here against Banks Island. And also, if you look at Wrangel Island here, ice was piling up on the, if you like, the upwind side of Wrangel Island. And then in the winter of 2021, one had the reverse. Now the thickness anomalies were distributed throughout the Beaufort, and now one had essentially the thickness anomalies in the vicinity of Wrangel Island actually being on the other side. Okay, so there were these two. So essentially, the point is that although we had thick ice in both of these winters, the processes responsible for that in the preceding cool season were actually different. This can be seen probably better here, where I've just taken the difference in the two winters. And so now you can see these very pronounced kind of dipoles. There's a dipole around Wrangel Island, there's this dipole in the Beaufort, and there's also, if you like, thicker sea ice in the last ice area, okay? And all of these are consistent with this anomalous circulation, where now we're essentially transporting ice in this direction here, okay? And so if you like, in 2021, in 2020, there was thicker sea ice in the last ice area as compared to 2021. So it's all a function, if you like, of the ice motion, which is in this case is driven by the synoptic scale pressure pattern. So another way to quantify this is to look at essentially the transport. So what I'm going to look at is the transport across the northern boundary of this area, and also the transport out across the western boundary. Okay, and essentially that then approximates, if you like, the sort of the increase or decrease of ice in the Beaufort Sea here. So what I'm showing you here, the solid line is the climatology, the sort of shading is plus or minus 1 standard deviation. The red curve is 2019-2020, and the blue curve is 2020-2021. And so you can see that there's a large degree of interannual variability, but by the end of the season, there's always typically transport out. So essentially the Beaufort is losing ice into the Chukchi, and that's again just the climatological circulation pattern associated with the Beaufort High. If you look at 2019-2020, you can see this year is quite anomalous in that the transport was into the domain throughout the whole season. So this year, in fact, there was essentially transport of sea ice from the last ice area into the Beaufort Sea. 2020-2021 was closer to climatology. In the early part of the season, there was some transport into the domain, but again, by the end of the cool season, again, the transport was out of the domain, okay? And if one looks at ice volume transport, one gets essentially the same idea. So now shifting, now what I'm going to look at, again, this is with PIMS data, looking essentially at the data from 1979. What I'm plotting here is a scatter plot of the cool season ice volume transport into the Beaufort Sea. And I'm plotting that against the June 1st ice volume anomaly in the Beaufort Sea. I've now split this up into two different regimes. The early regime where one had old and thick ice present, and then the new regime where one has young thick ice present. One can see that in both cases, there's a positive relationship. So that means essentially, if you transport more ice into the Beaufort, the ice volume in June will be larger. But if you notice, there's more scatter in the old regime compared to the new regime. And as a result, in the old regime, the R² value is about 15%, which means that the cool season transport explains about 15% of the variance. Whereas now, if you look into the new regime, although the slopes are very similar, now the variance is much higher. Now we're explaining upwards of almost 45% of the variation. So this is consistent with this idea that in this new ice regime, transport into the region plays an important role in determining the early summer ice volume. If you now look at the June 1st ice volume and then compare that to the September monthly ice concentration anomaly, here we again see essentially similar slopes, but in this case here, the amount of variance explained is about the same in the two regimes, okay? So both regimes explain about 40% of the variance, and this is consistent with this idea that thermodynamics is really the most important process for sort of explaining, if you like, end of summer ice concentration, although transport does play a role, it's not as important as the thermodynamic processes. So just to conclude, then around 2006, there was this transition from an old thick ice regime to a young thin ice regime. The summers of 2020 and 2021 had this interesting mix of both old and thick ice. In 2020, the anomalies were the result of the anomalous ice motion associated with the Beaufort High's collapse during the previous cool season, whereas the anomalies in 2021 were the result of essentially the climatological anticyclonic ice motion that transported ice from the last ice area into the Beaufort Sea. And there's evidence that recently cool season transport is playing an increasingly important role in the early summer ice volume. And thank you very much. And I'm happy to answer any questions.
Great. Thank you, Kent. Interesting. We have time for a few questions. So turn it over to anybody who has a question.
I see David Eric has already popped one.
Oh,
in
yes.
there, but...
Yeah, okay. So Eric, do you want to ask your question via your microphone or?
Sure. Yeah. No, I'm just referring when you were showing those linear relations. Yes, here we go. Increased scatter in the earlier time period compared to the later time period. But I also noticed you've got a much larger sample size, right? So I'm wondering what effect that is, 26 years in the early period and 14 years. I'm doing the calculation right in the later period. So I'm wondering what effect just sample size might have in influencing the perception of a greater degree of scatter, you know?
That's a really good question. And of course, how does one control for that? That's a really good point. I would just mention that the p-values are much lower in the later records. So that tends to argue that the signal is real, but it's a really good question. And I don't know how to control for that other than to try to sort of, subsample the earlier record and see if the scatter really is a function of that. My sense is that it isn't. I mean, looking at the data, of course, the scatter plots doesn't have the temporal variability to it, but the scatter was pretty uniform. It wasn't focused like in, let's say the 1980s or the 1990s. So it really was sort of evenly distributed through the time. But I really don't have an answer for that other than the p-values tend to argue that the R² values recently, even though the sample size is smaller, are actually more significant. But it's a really good question.
Great. Thanks. Any other questions for Kent? I've got one quick question then before we go to our next speaker, maybe. Yeah, it's very interesting. I think you're showing that there's a role for the from the winter and the early ice season in setting the stage and explaining part of what happens later in the summer in terms of ice, these ice, old ice and thicker ice coming into the Canadian Beaufort Sea. But that there is also, I would think, in fact, we looked at one year in a paper that we did a year or two ago for 2018. And that year was also in late summer. There was a lot of thicker old ice in the area of the Canadian Beaufort Sea on the shelf. And in fact, it got in the way of recovering our moorings. Our light icebreaker couldn't get through that ice and was delayed for several days. And that year we saw that the winds from July to September seemed to explain at least in part, why the old ice was there and was moved in to the shelf, originating from the western part of the ice area off the archipelago. So could you, is there two different things going on here, or is the preconditioning from winter and early summer the most important?
Yeah, so that's a good question. So I think that, typically speaking, the winter, ice motions, the winds are stronger in the winter than they're in the summer. So in that sense, one might think that there is that important role, but clearly, one can have anomalies during the summer, and they can move ice around. So I think it's it would be important to kind of look at the summers as well to see what's happening. My sense is that maybe in the summers you're just moving ice within the Beaufort, right, rather than bringing it in from the north or from the west, just because the motions aren't that strong. But it's definitely something to look at for sure. I mean, we have still a lot of variance that we're not explaining, right? So I think it's a really good question. But my guess is it's probably more that's internal redistribution rather than bringing stuff in from outside.
Okay, thanks very much. And I think we should move on to our next speaker. Helen, do you want to?
Thanks, David, and thank you, Kent. So we're sort of staying in the Beaufort Sea region. Our next speaker will be Matthew Asplin. Matthew is with ASL Environmental Sciences, located in Victoria, BC. So over to you, Matt.
Okay, great. Well, thank you very much, Helen, for the introduction. Can everyone see my screen okay?
Yes.
Okay, good. Let's check that. So good morning, everyone. Good afternoon for those of you in the Atlantic and Newfoundland time zones. So I'm here today to talk a bit more about atmospheric forcing of wind-driven regional sea ice motion in the winter and early spring in the Canadian Beaufort Sea. And I think as we get into this, it'll become apparent that it's what I'm looking at here is of course, some of the recent work that David and I have been working on with in the last few years with our more recent data sets. But I also want to go back in time to an incredibly rich and detailed data set that we have from the 2009 to 2011 period that was collected as part of a larger academic industry partnership. So we'll just step right into this here. So the motivation, this is part of a bigger project that we are conducting at ASL Western Beaufort to better understand atmospheric forcing of sea ice motion during the winter, corresponding with the transition from a multi-year to first-year sea ice regime. And this specifically is looking at wind forcing response to winter sea ice cover at different times during the winter, and where we see some response to sea ice when the ice is a little thinner and not quite fully developed, versus late in the winter and early spring when it's at its maximum extent, approaching maximum thickness, and may have less of a response. So this is, of course, covering important interests in changing dynamic sea ice processes, rafting, ridging, sea ice lead formation midwinter. And it has implications for the summer melt season and the summer navigation season, with relatively thicker zones of the area that have been made thicker by pressure ridging and rafting and whatnot. So represents the presence of ice hazards that can become mobile and move around. So yeah, so this is a feature that we've been seeing, it seems, more frequently in recent years. Particularly, it feels like been seeing this just about every year since 2007. That might be just biased, but that's when I started my PhD. But what we're looking at here are two animations of the same area. So apologize that these aren't facing north, they're sort of more like facing south. So this is Banks Island down here that's rotated on its side. And this big body of open water to the left here is Amundsen Gulf. And what we're seeing here is in both cases, I don't have a date on the left one, but this is March, April into early May. We're seeing these big wide scale regional wind forcing events that are causing the sea ice to open right up during the midwinter season, thereby exposing a lot of open water and a lot of area for rapid regrowth of ice, which can then be subject to dynamic forces if those winds change, and the existing ice pack can come back in and crush it and whatnot. So really interested in what's going on with this phenomenon. So in a period of declining sea ice, I think Kent covered this really well. This just a recent figure of ice age pulled from the National Snow and Ice Data Center. I really want to focus in though on this period here. So as you see with the record, back in 2007 to 2012, it felt like we were falling off a cliff. But the trend line, although it's still negative at about 81,000 kilometers squared per year, perhaps that should be per decade. But in any case, we're starting to see what appears to be maybe a bit of a stabilization as we're reaching our new first year regional sea ice regime. That said, the trend line is still negative. So we're getting into this, what's next in the next 5-10 years here? Are we indeed going to see a sort of a bouncing around a new somewhat normal for September minimum, or is it going to continue to go? So looking at wind trends, the trends in the area, this study I do admit is a little old now. It's from 2012 from Statistical and Zhang, but overall we're seeing a trend of increasing winds through the winter months here. So somewhat weaker in January, but more so in February and March, as well as April. And again, back to the late fall, we're seeing a particularly stronger trend in increasing winds in October and November. But we're going to focus mainly looking at the winter season here. So a tool that I like to use in a lot of my past work and still do from time to time is principal components analysis and k-means clustering to create synoptic types, which are essentially a group of like sea level pressure categories that can, whoops, almost have a timer on there, but that can best describe the climatology of an area. And in this case, we use a 7 cluster solution that explains 91% of the variance, and there's 13 types that are identified, and represents the reduction in the mean spatial distance between a cluster solution between 9 and 20. So I went with 13 years as optimal, and the relative frequencies at their time of year are given on the chart on the right here. So now linking this into more recent work by David and our group. So we have been looking at trends toward reduced ice coverage in early fall to mid-late spring. We're seeing trends in the start and end dates of ice velocities and when ice is moving. And we're also seeing alternating winds from the east and the west, with the typical durations about 4.2 days from the east, 2.6 from the west. So we are seeing these easterly wind events that I think Dave touched on a bit, and particularly in the late fall and in the spring, in March through June, we're seeing these events. And we're also seeing this variation between sites of reduced ice motion at inshore sites in winter and spring, and a trend at the mid-shelf site to a large increase of ice speeds in late winter and spring. So just a recap of some recent findings. And again, this is, I'm not going to go through this whole slide verbatim, but essentially this is looking at the analysis that we did of recent wind forcing events using MSC Beaufort hindcast wind wave data from 1999 to 2015. And then we filled in time after that with ERA5 reanalysis winds. We were able to compute our east versus west events from that switch, which Dave has used in his talk. Now, what I want to do now is go back in time a little bit to the 2009-2011 ArcticNet Industry Partnership Program, which was a partnership between the ArcticNet universities as well as a number of large oil companies that at the time were intrigued by the rapidly declining sea ice and the relatively high price of oil. If you think it's high today, I think we were at $180 a barrel at one point back in those days. So there was some interest in exploring this area. The government at the time was quite supportive. So we benefited from this with now having this incredibly rich, spatially dense data set of offshore moorings, which have a suite of equipment on them, the ASL ice profiling sonar, ADCPs, which can be set in bottom track mode to get ice velocity, and water quality sensors. So using the data from this, I did a bit of a particle displacement analysis looking at the different sites. So if you keep that map in mind, there were, I think, 9 different sites that were used. And so as you can see from this particle analysis, everything's sort of moving from east to west. Not much of a shocker here, really, but we do see a bit of spatial variability, though, between the sites, which again is what the value of this spatially dense network of moorings provides. It allows us to do a more sort of mesoscale analysis of spatial response to wind. So comparing to a broader climatology for the period, so this was the time in 1979 to 2009 climatology showing sea ice motion versus what we saw in the winter of 2010 and the winter of 2011. So these are January through May, and particularly you see in 2010 in February had a pretty strong response in the ice motion here. So again, these are ice motion vectors from the Polar Pathfinder daily 25-kilometer ease grid, and they're available through the link here, the data set rather. Those are speeds in centimeters per second. So we did a little bit of regression analysis on this, and in fact, I'd like to extend this to the more recent data sets that we have from other programs, and look at regression of surface winds to the ice motion vectors that we have from our moorings. And also keeping in mind currents. I heard that question about currents in the previous talk, so I'll just address that briefly. And this is using regression methods that of Shimizu et al. 2014, which is basically fitting the wind forcing to the sea ice velocity and looking for a forcing magnitude and a turning angle, as the sea ice will turn with to the right as a result of friction and Coriolis. So this is a summary of regression done within the synoptic types. So synoptic type 13 had too few samples, so I dropped it from here. And what you can see is a number of types have a very different response factor, and also the R-squared fit factor in terms of how well they match up with what we're seeing in terms of predicting a response and turning angle within the sea ice for a given type. So we see the strongest R-squared values are coming from types 5 and 6 and 7, as well as to a degree 11. And I varied these across 2 sites, which are, I have to go back to the map to show you where those are, but the idea there was to get a bit of a greater variability in terms of where what we're seeing in terms of response. So overall, the site H is showing more of a response. I believe site H was further offshore, if I remember correctly, but I might just go back to my map just to refresh my memory here.
And Matt, while you're doing that, you've got about 1 minute remaining.
Okay, yeah, no, where'd my map go? Yeah, there we go. So site H is here and site A1 is here. So these are the 2 sites that are along the shelf. Okay, so apologies for the backup there. So Ocean current forcing. So yes, this was something to look at real quick. Basically did this regression analysis without ocean surface currents and with surface ocean currents. And the difference in terms of R square values was almost negligible. So the it's really the wind is really a predominant forcing factor here. Probably if I had to estimate it, it would probably be about 90 to 95% of the forcing is coming from the atmospheric forcing rather than the ocean currents. But okay, so in summary, the long duration winds are moving ice and they're higher than average speed and directionality. We've seen a lot of easterly wind events. We have of course, a lot of coverage here in terms of spatial coverage of wind forcing events, as well as temporal coverage, as we can go back to our mooring data sets from 2009 and prior. In fact, we have data from ice moorings in this area covering 1999 to present, if we include our collaborator Humphrey Melling at Institute for Ocean Sciences. So yeah, a lot more great potential work to be done here, and look forward to presenting on it in the future. So thank you very much.
Thank you, Matthew, for your presentation. We may have time for a quick question if someone has something. Or maybe while someone is thinking of their question, I just wanted to acknowledge having the two presentations in this session from ASL Environmental Sciences. So it's two presentations from the private sector, together with those presentations from our academic and government scientists. So I think it's made a really nice complement of researchers from across the spectrum. Any questions for Matthew? If not, we're more or less on schedule, I think, David.
Yeah, I think we're doing pretty well. So, well, but to stay on schedule, maybe we should introduce our final presenter today in this session. And this presentation is from Minghong Zhang, who is at the, I believe at the Bedford Institute of Oceanography. And Minghong is going to be talking about seasonal predictions of the open water season in the Baffin Bay region. Minghong?
Yes, yes, I share my screen just a moment. Yeah, this one. Can you see my screen?
Yeah, it's good. If it goes in full presentation mode.
Yes, okay. Yeah, okay. Hi everyone, my name is Minghong Zhang. I'm from Bedford Institution of Oceanography. Today I'm going to present one of our recent studies, the seasonal prediction and predictability of summer sea ice in the Baffin Bay region. This study is supported by Transport Canada. Will and Zhenxia are my co-operators. How can I close this? Sorry, I need to close this. Yeah, okay, thank you. Oh, sorry. In this talk, first I will give a background introduction, then I will talk the data and the methodology. In the third section, I will introduce our statistical forecasting model. In the fourth part, I will discuss impact of large-scale atmospheric mode, North Atlantic oscillation, and East Atlantic pattern. At last, I will give a summary. The seasonal forecasting of ice condition is becoming increasingly important due to the social and economical interest. The upper left panel shows the shipping route of the Baffin Bay region for the summer resupply to northern settlement, and the upper right 3 plot shows sea ice extent in June, July, August. We can see over the Baffin Bay region, the ice free in August. So our forecasting month is sea ice in July. The bottom 3 panels shows ocean circulation and multi-year, 4th-year ice coverage over the Baffin Bay region. We can see the southward Baffin Island current and northward West Greenland current. Also, we can see most ice in the Baffin Bay region, the 4th-year ice. But there's some thicker multi-year ice of the Baffin Island region from Arctic. So here we use atmospheric realized data set ERA5 and UNCEP UNCARS realized data. Ice data is from National Snow Ice Data Center, including ice concentration and ice motion. We also use oceanic realized data, CMOS, and the Arctic Ocean physical realized data set from European Center. Here we build our statistical forecasting model using a multiple linear regression model. In our study, we choose 3 precursors, the Winter North Atlantic Oscillation, NAO, and the Winter East Atlantic Pattern, and the long-term linear trend. The left 2 columns shows the regressed sea ice concentration in June, July against the winter NAO. Here, the sea ice concentration is lagging by 15 and 16 months. In another word, the NAO and the EAP is leading by 2 winter time. We can see there's significant positive sea ice concentration anomaly associated with the NAO and EAP over the Baffin Bay region. The right column shows the long-term linear trend of sea ice concentration over the Baffin Bay region during the last 5 decades. We can see very robust decrease in the sea ice concentration over the Baffin Bay region. Here I wanted to show our statistical forecasting model. In this plot, the red line is the estimated sea ice area in July, and it shows a good correlation with the observation, the black line, especially after 2000. This mode has a very high correlation coefficient, 0.72 with the observation. So it accounts for about 52% variation of the July sea ice area in the Baffin Bay region. And it has a leading time of 16 months. We also forecast the sea ice area in July 2021, the red cross. It is very close to the observation. The arrow is very small, about 0.8%. We also produce a spatial pattern, a spatial map over the sea ice concentration in July over the Baffin Bay region using our statistical model. This slide shows the regression coefficient of the NAO, EAP, and the long-term linear trend. The next 2 plots shows the correlation coefficient and the residual standard error from our statistical model. If we look at the correlation coefficient, we can see it varies in a range of 0.6 to 0.7 over most of the Baffin Bay region. And the residual standard error is also smaller than 2.6. And this suggests the good scales of our statistical model. We also conduct the forecast of sea ice concentration in 2021. Let's look at the middle plot. This is a predicted sea ice concentration by our model. We can see it exhibits a very similar spatial pattern as the observation. In this part, I will talk the impact of NAO. Most of you are very familiar with this leading atmospheric circulation mode. The upper left panel shows the sea level pressure and the surface wind of the positive NAO, and upper right plot shows regressed CS concentration in January, February, and June, July against the NAO. The CS is lagging by 1 year. We can see very significant positive CS concentration anomaly associated with the NAO over the Baffin Bay region. The bottom plot shows the time series of CS area in July and the NAO index. We can see overall on the decadal scale, the variation of the CS area follow the phase change of the NAO. This slide shows the lagged correlation of CS area with the NAO. We can see the winter's NAO index is significantly correlated with the CS in the Baffin Bay region in the same winter. And this collection persistent into the following second year. I think most of you may be very familiar with the impact of NAO on the North Atlantic Ocean. Due to the time, I cannot talk it in detail. Briefly, during the positive NAO, there's an increase in the oceanic heat loss to atmosphere in the subpolar gel region, and a strong cooling in this region. As a result, the deep convection is intensified, and the sea level drops over in the subpolar gel region. This is needed to increase in the southward Arctic outflow through Larry Strait and Davis Strait, which carries more ice from Arctic to the Baffin Bay region. Also, there's less warmer water. The warmer North Atlantic water are transported by West Greenland current. It causes less ice melting here. This whole process persists about 2 years. In this section, I will discuss the impact of EAP. The upper left plot shows the sea level pressure and the surface wind of EAP in the winter. EAP is the second leading UF mode of North Atlantic atmospheric circulation. The upper right two plot shows regressed CS concentration in June, July against the EAP. Also, this CS is lagging by 15 months and 16 months with the EAP. We also can see the significant negative positive CS concentration anomaly over the Baffin Bay region. The bottom plot shows the CS time series of CS area in July and the EAP index. We can see overall this variation over the CS area also follow the phase change of EAP. We also show the lagged correlation of the CS area with the winter EAP. You can see different from the NAO, the forced peaking correlation coefficient of CS area in the Baffin Bay region with the EAP appears in the July of the following second year. And this positive correlation persists into the following years. Here I will discuss the impact of the EAP briefly. And the intensified loss wind associated with the positive EAP would remove the ice in the loss water region faster. It need to more loss water polynya, also more rapid ice growth. This contribute to increased in soil injection in the northern water in the loss water region. We can see it from the upper right panels, the regressed salinity of the surface layer against the EAP. And such increased salinity in the lost water persist for at least 2 years. You can see the regressed salinity of the surface layer in the following second winter. Such salty water such salty water would delay the ice growth process. Also, it will slow the ice motion in the following second winter. As a result, there's more ice flowing from Arctic to the Baffin Bay region after the break of the Northern Ice Bridge. Okay,
you have about 1 minute remaining.
Yes, let's go to the summary. So our forecasting model using the winter's NIO and EAP and the long-term linear trend. It had a lead time of 16 months. It is estimated CIS area had a high correlation coefficient with the observation, which account for 52% of the variability. The spatial map of the estimated CIS concentration using our forecasting model shows considerable scales in predicting the observed CIS concentration in the Baffin Bay region. Also, we investigate the physical process of the impact of NIO and EAP. Thank you for your attention. That's all. Welcome your questions and comments. Thanks.
Well, thank you, Minghong, for your interesting talk. And are there any questions for you? Yes, Fred.
Hi, David. Thanks for the talk. Yeah, I was trying to understand. Sorry for my ignorance. What is the EAP again? How is it defined?
It's East Pacific pattern. It is the second leading UF mode of winter North Atlantic atmospheric circulation. It accounts for about more than 20% of the variance of North Atlantic winter circulation.
Okay, so the first mode will be the AO in that case, and this is the second mode. Is that correct?
Yes, yes. NIO is the first leading UF mode.
Okay, thank you.
Thank you.
Any other questions for Minghong?
If I can make a second one.
Yes,
David?
Go ahead, Fred.
The so you were looking at lags of 1 or 2 years. So were you suggesting there's some kind of preconditioning involved? What explains the long lag, I guess?
Yeah, I also consider the precondition of the CIS in winter or the preceding winter. But we take a look at the CIS thickness and look at the collection of CIS thickness in winter with the summer CIS. But the problem is over the Baffin Bay region, most ice is the first year ice. And the ice is ice come from Arctic. It's not, the thicker multi-year ice from Arctic is usually flash away in the summer. So there's no good persistence of the CIS thickness over the Baffin Bay region. So we don't include the precondition of the CIS, for example, CIS thickness here.
Okay, that makes sense. Yeah, thank you.
Thank you.
Okay, well, thank you very much. And I think we are just about out of time. We've got, yes, we got 2 minutes left in our nominal time slot. I think a reminder that the 2 poster papers that are attached to this session, but that we've already seen previews of from Madeline and Caitlin, there is another session in which those papers will be presented and discussed. And Helen, do you know what the time of that session is? I believe it's tomorrow morning.
That's right. Yeah, it's 11:45 to 12:45 Central Time. So
Okay.
I'll let everyone figure that one out. But yeah, so it's tomorrow, 11:45.
Okay, very good.
And David, in addition to a reminder about the poster session, I would like to put a promotional message out for the public lecture this evening.
Oh, yes.
On Arctic science. I would encourage everyone to join us if you can. Eric Oliver will be presenting. I've heard him before. He's a great speaker, and he's going to be, his topic is bridging knowledge systems, scientific and Inuit knowledge on the ocean and sea ice. So if possible, that is at 5 o'clock, I think, Central Time. So if anyone could join us for that. And finally, from my side, just a thank you to Alana for being our technical support on this session so that David and I didn't need to worry about letting people in the room or whatnot. So, and with that, just from my final words, just thank you everyone for joining us. Back to you, David.
Yes, and I'd echo that. Thanks to everybody who's all our speakers today. They've been very interesting talks, and to all of you who have asked questions. And I think there's still more discussion to come on these Arctic papers. And so I'd encourage everybody to reach out more informally between presenters and attendees of this session and continue the dialogue. So thanks again for attending.
Goodbye, everybody. We'll